Hi everyone, my name is Neil Johnson. I'm just a sports analytics developer at Disney Analytics. And today I'm going to talk about parsing player tracking data from broadcast video. Video is plain, that's good. That's not always the case. So just a couple things up front, or quick things up front. I will do this with basketball video, but this is sport agnostic. And there's a lot of ground to cover, so I'm going to try to go into as much detail as possible, but we'll see. And then yeah, so let's just get started. Okay, so what are the current problems with available player tracking methodologies? It's expensive. That means fans and academics usually can't afford access to it. You can't go back in time with it. You can only process games as they're happening live. And you can't add features like pose estimation or other things that aren't already pre-programmed into your hardware configuration. And then lastly, the process isn't transparent to us. We understand at a high level how they work, but they're still kind of black boxes to us. So my new methodology proposal is to use non-stationary camera feeds like broadcast video and some open source computer vision software libraries to create your own player tracking data. If you're a person who works in Python and does machine learning stuff, you should understand everything I'm saying and should be able to pick this up pretty quickly. So I'm labeling this CV tracking, which is computer vision tracking for short. And the other goal of this is I want to create a new approach that's transparent so the process can be reviewed and improved. I want everyone in this room to kind of take it and run with it. And then I want to create that blueprint so player tracking is much more accessible to outsiders. Someone who isn't with a team in a major sport or works for a team in a smaller sport that doesn't have the budget to buy these big, expensive tracking systems. So what are the inherent benefits of CV tracking? We can retroactively create the data from any broadcast video. There's no pressure to process the game live, and we don't have any customers here, so we can prioritize quality versus availability. Let's see. This will only cost man hours, not tens of thousands of dollars. So there are parts of this at this point that will require human intervention to make sure things are working as is. And in the future, we can definitely streamline those to minimize that as much as possible. We don't need access to the facility that the game is being played in. We don't even need to be in the same country that the game is being played in. We just need to have that video of the broadcast to apply this methodology to it. And lastly, we don't need to stick devices on the players' uniforms or pads. We don't have to worry about them falling off, running out of batteries, players having placebo effect worries with them or anything like that. So we don't have to worry about that at all with this. So drawbacks and disclosures, like I said, being transparent here. CV tracking works on the assumption that the source video shows enough of the game, enough of the action, is on the action enough. I mean, inherently in a broadcast, they're going to show the most important parts of the game. They're going to follow where the ball is and where all the action is, right? So as long as it's doing that enough, we can fill in the remaining gaps. This talk doesn't cover ball tracking. When I submitted this work, I hadn't done any work on ball tracking. Since then, I've actually done a little bit, and I think there's a path forward there. So maybe that's something I'll present on in the future. And there have been attempts at accomplishing different types of CV tracking already. Some are fairly successful. As far as I know, SportLogic does a good job with it. And I've only seen this specific approach discussed in theory before. And the goal of this presentation is to be more practical. So what is the high-level approach? I'm going to talk about each bullet point, and then I'm going to go into depth in the next slides. So the first part, we're going to derive separate data sets from the video. The first one is called player pose estimation, which we'll use to calculate center mass. Next part is court mapping. We're going to use OpenCV's template matching function to identify where the court is in each video frame. And then game context. Basically, we're going to kind of do optical character recognition on the scoreboard to understand, period, game clock, shot clock. And then once we have all that, we're going to merge everything together to compile that, resulting player tracking data set that we are looking forward to. All right, so the first part is parsing player information from the video. So to do that, we're going to use what's called pose estimation. There's a bunch of different open source multi-person pose estimators out there. The one I like the best was called Alpha Pose. And then it has supplemental software called PoseFlow, which tracks people and their poses across video frames. So a pose estimator is just going to take a single image and try to identify all of the people in it and where all of their specific body parts are. So that's where you can see a skeleton overlay for each person in the video. And then PoseFlow is going to map each video frame together to say that this is that person from previous frames. So that's where you can see the skeleton overlays stay the same color for each individual. That's signifying that it knows that it's the person from previous frames still. So like I said, this one seems to work the best in crowds in my experience. You can use a CUDA-enabled GPU to process the video in real time. Since I submitted this, they've gone it up to like 25 frames per second, depending on the configuration. And it has a PyTorch version that makes it easy to set up, so you don't have to compile the code yourself and kind of debug all the issues depending on your configuration. So we're going to identify players in video with this. The first step you need to do is split the video into segments where each segment is just one continuous shot from a single camera. Then we're going to run Alpha Pose's pre-trained models on that video, frame by frame. So we're going to convert it into a series of images. Then you're just simply going to take the Alpha Pose output and feed it in the PoseFlow. And then once you do that, I recommend visualizing the results to confirm that it's working as intended. So what you can see, there's a lot going on here. So you can see it's trying to identify every single person in the video that it can. And it's picking up a lot of people in the crowd too. The head, or the numbers on the heads are representing their PoseFlow ID, so that's showing that this is the same person from previous frames. And once you have that, you can start to only focus on the players on the court. So that's where, like I said, you want to isolate the players in the video next. This is the first manual part of the process where you want to map those PoseFlow IDs to your own IDs for the players. So I just use alphabet letters so you understand who each person is, what team they're on, all that type of stuff. And then once you have that, you can calculate the center of mass data and finish this part. So like I said, Alpha Pose returns up to locations up to 17 body parts per pose, so like an X, Y, and then a confidence interval. And for my center of mass calculation, I basically took the average location of their ankles. Other systems use like hips or their midsection for that. So you could do either, depending on what you want. And so what I did was, if ankles are present, then I can estimate the location of the ankles, right, using the height of the pose over time and like their knee values or other body parts. So it's a little hard to see here. It's a little bit small, but you'll see red dots at the bottom of each pose, and that's signifying where the center of mass is in the video frame. So that completes the first part. The second part is parsing court information from the video. So what is our approach? We want to know where specific parts of the court are within the video so that we can then take those coordinates of the court and the people in the video and transform that into our resulting player tracking data. And that's because we know the measurements of a basketball court, right? So we know what those will be in the player tracking coordinate system. So to do that, we're going to use OpenCV's template matching function. This is a very simple function. It basically just takes a template image and attempts to locate it within a source image. So you can see on the left, it's got the template image in the top left, and the algorithm literally just moves it across the source image and then tries to return the location it is at. So we're going to use this to figure out where the court is in each video frame. And to make this work better, I did some pre-processing to increase accuracy. Basically, what you want to do here is just find a way to emphasize the lines of the court and de-emphasize everything else. So what I did for my instance was anything that was close to white, I made true white. And then everything else I made black. And to do that, I used a photo editing software called GIMP and just wrote a batch script to process it for every single video frame. So as you can see, I got the template images on the left, so we got the center court logo, we got the paint on the right side. We're going to apply that to the source image with the template matching function, and then the result is the coordinates of those template images within the source image. So once you do that, you can do that to every frame, and you can revisualize it. And what you want to do is you want to have more than just one template. So I think I have about 7 here, and we want to make sure we're finding at least one template almost every single frame. If there's small gaps where you don't have any, that's fine. And what you also want to do here is whenever there are false positives in the matching, you want to take those out yourself so we're not messing up some of our work later on. So next part, this is the easiest part, is just parsing out the game context. So this just helps you understand where we're at in the game for each frame of our data set. And that's where, like I said, I'm using PyTestRack to perform OCR, optical character recognition. Every broadcast is going to have relevant game information on the screen. So for basketball, it's period, game clock, shot clock. And we're just going to apply PyTestRack to that specific location on the screen. And once we have that, it's just a simple script to kind of parse that out, scrub it, and then serialize it so we know for each frame what this information is. So now we need to merge everything together, right? We've got the 3 parts. Now we need to create player tracking data. So what we want to do is, in this point, is transform coordinates from the video coordinate system to our standard player tracking coordinate system. So for a 720p video, the x-axis would just be 0 to 1280, and on the y-axis, that'd be 0 to 720. If you're not familiar with the standard coordinate system for NBA's player tracking data, an NBA court is 94 feet by 50 feet, and 1 unit in the system is just 1 square foot in real life. And center court is 0, 0. So on the x-axis, it'll be negative 47 to 47, and on the y-axis, it'll be negative 25 to 25. So since we are working with 2 independent planes, we can simply create a function to convert a set of coordinates from one plane to the other using a series of affine transformations. And that's because we know the exact location of the coordinates of the court features we have mapped in both our player tracking coordinate system and our video system. So we can use that to create these affine transformation functions and then apply that on the coordinates for the players in the video system. And once we do that, we will have our very first iteration of player tracking data. Success, right? Oh, I mean, it's kind of looking rough right now, but that's okay. You'll see that there are points where it's disappearing right now. There's a little bit of jitter in this stuff. This is the first iteration of it. So that's where you realize we still have some work left to do. So like I said, the data is noisy at this point. Players are disappearing for frames when they're not on camera or we don't have any court features mapped. Some players' coordinates are just simply off for a certain period of times, like they're kind of all have the wrong offset or something. And that's okay. So that's where we're going to do some scrubbing, some interpolating, and some other solutions here to get it up to speed. So most of the problems are solved by just applying filters. A common filter will just smooth out that noise. So you saw that kind of jitter when a player's on a certain trajectory. That'll make it a nice, smooth trajectory. And then we can apply an educated guess between 2 known points for a player to fill in those missing gaps. So right now I have a very basic approach to that, and I have some ideas on how to do that better too. Some of this will require the human eye to just make sure like every player is still mapped correctly at this point. None of the above filters are overcorrecting and hurting the data quality. And just in general, that nothing looks super wonky at this point. So once you do that, you can take a deep breath and realize everything is going to be okay. So on the left is what we saw before, and on the right is after doing the scrubbing process. And there are points where the dots are going to a lighter color, and that is when we are filling in the gaps for those missing, for the missing values for the player's truth location. So at this point, things are definitely looking a lot better. And what I use to fill in those gaps is just like a linear function for the time for which we last saw them and where they came back, and just filled it in. And that actually works out better than I thought it would, but I do have some thoughts on how to improve that too. And then we'll go back to the main video at the beginning. Looking good. So the original video was in 60 frames per second. So for doing this whole process, I downsampled it to 15 frames per second to help speed things up. And then the resulting player tracking data, I then upsampled back up to 60 frames per second for this. So at this point, I think things look really good. For me, this is kind of validating the process. It's showing that things are working well enough, and with some more research and development, we can make it even better. But at the same time, we should still do some testing, some accuracy testing, right, and see what that results in. So I took a stab at that. So I applied this to an NBA broadcast. I asked a group of random people to verify how often CV tracking was, for a given player, was within 1 foot of where they should be. And I gave them the display of the court diagram with the coordinate location for each player, and then I gave them the video frame that it came from. So after About nearly 300 samples, the CV tracking was within 1 foot 94.5% of the time. Honestly, that was better than I thought it was going to be. So as a control, I did that with the NBA leagues provider player tracking data. I gave the same prompt. I asked the same set of random people. And to my surprise, it was only within 1 foot 92.1% of the time. But I'm going to say this right now. I don't think my system is definitely not better than theirs. I think that speaks to a couple things. I think that speaks to 300 samples not being enough. It's too small of a sample size. I feel like you would want 3,000 samples or even 30,000, but I spent a lot of time just trying to get people to do 300, okay? And then I think it also speaks to, we don't necessarily know everything behind these processes for these player tracking systems, so we shouldn't necessarily assume they're 100% either, but they're probably still 99%, right? So in light, not being able to have more people kind of do some validation on my own, I want you guys to download the data for yourself and to decide for yourself how good it is or isn't. I want you to scrutinize it and to let me know. So at this link, there's a zip file, and it's containing player tracking data for our 2-minute segment. The source video that it came from, that same moving dot animation video I showed you, and then just a mapping file for the players so you know who's at who. So what are next steps? Biggest one's to identify where the ball is, right? So like I said, since I submitted this paper, I have spent a little bit of time on that, and I definitely have found the start of an approach where we could definitely estimate where the ball is. It won't be super precise, it might not have the z-axis, but it could still help you do your player tracking level of analysis on this data that you already do. Use a proper ghosting model to fill in the gaps instead of just a linear fit. So a couple years ago, the Disney Research Group presented a paper called Ghostbusters, which was a play on the word Ghostbusters, and what they did is they just created a ghosting model for one side of the ball. So if you had the 5 players on offense, where should the 5 players on defense be, and vice versa? I think you could do a same approach, but have a series of ghosting models for the n amount of known players you have to input into it. So you can ghost where the 10 minus n players should be on the court. I think that would work really well. And then to utilize this post-estimation data, this is a whole new data set we could use. I think it could really help the fidelity of our analysis. And you could do simple stuff like just getting the player orientation where their heads, directed where their hips and shoulders are. I think there's a lot you could do with that too. And I've actually already done one step with this. So this was something I tweeted out if you were wondering what I was tweeting about. So this is helping the process of player mapping by automatically isolating the pose flow data to people on the playing surface. So on the left is kind of what we saw before where everybody's getting mapped. We're mapping all the people on the bench and all of the fans as much as we possibly can. I just created a simple script to basically filter out all of the poses that I know very much aren't a basketball pose. If you're sitting down, you're not playing basketball, right? So it's pretty easy to automatically eliminate those. So that'll make the manual mapping a lot more easy, and it'll also decrease computational time. And then, like I said, this can be applied to other sports. So I created this for the Blue Jackets Hockey Analytics Conference to show that you can do this with other sports. You can do this with hockey. So we're mapping the court features or the ice features on the right, and we're getting the poses of the hockey players on the left. So those are the 2 fundamental steps to create this. Now, each sport is going to have different challenges. Some sports I think are easier to probably do this on than others. I think soccer is probably going to be the easiest one to do, but depending on your situation and depending on your desire, you could definitely create your own player tracking data for any sport with this approach. So that's all I have at this point. I'd like to thank everybody for coming here. Here's my contact information. I'd love to hear your feedback. I really want people to take this and run with it. There's all these different avenues that need to be improved on this. It's a big effort. So I want other people to put their own work. And then, as before, I had that link for the sample data. So here it is again if you didn't get a chance to save it. So download it, take a look at it, scrutinize it, and let me know. That's all I have. Thank you guys for your time, and I'm ready for questions.
All right, if you have a question, raise your hand. I'll bring you the mic.
Hi. How are you taking into account player height
So how tall are they, and also are they jumping, or are they on the floor? Is that taken into account?
Yes. So, I mean, with player height, that doesn't impact calculating like center of mass calculations at all. Jumping, if that actually is something that I haven't covered yet in this, if you watch that video again, you'll see like a big jump will definitely kind of skew the coordinates. But that's where, with the pose estimation data, I think what you can do is start identifying actions, and you can start identifying like he's in a jumping motion now, and you could kind of correct for that. So with some more time, I think that's something that could be done pretty easily.
All right.
Just along those lines, have you seen any like less accuracy with taller players in this? Because I imagine that the training data set for these models in general were not 7 foot tall people.
It's interesting you guys both say that. I didn't notice that at all. And then, so this, I'm using just the vanilla pre-trained data that comes with the pre-trained data set that AlphaPose used. You could also build up your own if you wanted to as well. But yeah, that's where it works really well as is. And then on top of that, since we're doing a series of frames where the action as time goes on, there are any weird one-off frames where it's looking kind of weird, we could do it at 60 frames per second if you wanted to. So you could kind of smooth over those outlier instances, but I didn't notice those.
So the template matching portion of it, did you run into any challenges with that, I guess with reflections or just different courts that were difficult for that? And then have you thought of any like automated techniques for it?
So yeah, there are a couple of parts to that. It is something where for each surface or court that you're going to do this for, you're going to have to create your template images once. But once you have that for a specific court, I did notice with different broadcasts from different broadcast companies and even different video qualities, it would still map it really well. In terms of like shadows on the court or like in football, shadows from the stadium, that is a challenge you're going to have to control for. But what I noticed is you could also create the templates for those shadows as well and then see which one results in a better response. One other challenge that I didn't necessarily cover in this is the template image is just going to look at the template at one size, right? So if there's some zooming in the camera, you're going to have to kind of scale your template image to kind of match that as well. So that does increase computational time, but I found that was a pretty quick thing to kind of put in.
I think you just started to get into it, but can you identify any characteristics of sports that make them either easier or more difficult to track? Like you mentioned, you thought soccer might be the easiest one, but then you showed a hockey example.
Yes, so I think soccer is the easiest because the perspective of the camera is so far back, and the action, the pitch is so wide. The action doesn't really have players clustering a lot. So in computer vision, a problem is called occlusions. People are in front of other people. And the jumping in soccer isn't, like, people aren't moving on their z-axis a lot, right? Hockey, so I think there is a challenge there where just the nature of the broadcasts, they got to swing very far to the left and right because ice rink is bigger than a basketball court. But at the same time, both of those sports, the playing is a lot more simple. There's not like a wood grain to it. There's not random advertisements coming in off the court. NBA teams have alternate courts now. So they all kind of have different pros and cons. I do think American football is probably the hardest, especially from a broadcast. Maybe if you had the all-22 camera, that would be worth kind of pursuing. But at the same time, there's just going to be a lot of like clustering and occlusion because of the nature of football. Everything ends in a tackle. It starts with the lines being all on top of each other. So I think maybe you could do something with respect to like the skill positions, like where the quarterback, the wide receivers, defensive backs, corners. But yeah, it would just kind of depend on that as well.
Thank you.
All right, we have time for one last question.
I'm curious, how long did this take you? It seems like
Yeah. So that's a good question. I had very not fancy hardware, so it definitely took a long time. For a 2-minute video, just doing like the alpha pose on it, I think at 15 frames per second, I think at the best that I got it to was about 6 hours. That's a long time, right? But I did do a lot of research into like theoretical best cases. So if you had, a lot of nice graphics cards, you had unlimited hardware, or just the latest and greatest, and if you, for the entire process, you had multiple people that you could task to do work on it, you could get it down to about 12 hours. But yes, this is part of it, that it's not, it's going to be computationally intensive at this point. And that's the other thing with this whole space, with this computer vision space. Pose estimation really wasn't a thing 5 years ago, or if it was so inaccessible because it was so computationally challenging. And that's kind of rapidly changed since then. So at the same time, maybe a couple years from now, those computational requirements will become much more accessible to us, and it'll be much easier to do.
All right, please give it up for Neil.